Hello, this video is going to look at how to solve second order differential equations where all the degrees of the terms are different. I have to say that this method won't always work. This is a bit of a trial and error type approach, trial and improvement. What do I mean by the degrees not same? Well, have a look here. Here's an equation and I've got an x here and I've got an x squared there. I've got a p and plus qx there and I've got an x there. So these, we can't just put in a y equals x to the n and it would all definitely fall out. What we are going to do is look at a substitution that will help us do that and see if it results in a nice well-behaved equation like this. Yeah, z here is a function of x. Okay, so let's have a look and see what happens here. First thing I'm going to say to you is, in an exam they're going to tell you what this power is to go into our solution, but in the real world we won't know what the power is of x and we have to work it out for ourselves. So I'm going to take you through that. So if I assume for my trial solution or simplification that y equals x to the n, then the differential is going to be that and the second differential is going to be that, just using our algorithm. And I'm going to substitute those into my differential equation. Here we go. So I'm replacing the d2y by dx squared with the second differential. I'm replacing the dy by dx by the first differential, and I'm just replacing y with the original function that I'm using as my trial function. And what you can see here is, after a bit of tidying up, we get our three terms and we've got different powers of x to the n. So I've got a power of x to the n minus 1 here from this term, so that's going to there. I've got a power of x to the n from this term here, and this one in the middle is a mix. So I'm getting the 2 times the x to the n minus 1 is going to come over here into this term, and the minus 4x times x to the n minus 1 is going to end up in here. So once I've done that and I've collected up, I get an equation, a very neat little equation here, but it's in 2 powers of x. I've got x to the n and x to the n minus 1. Now, if I wanted to just get a simplification, I would just want one of these coefficients to go to 0. And that would just give me 1 power, wouldn't it? But if I wanted a full solution, i equals 0, I'd want both of these coefficients to be 0. So I'm picking my values of n to see when that will happen. So I've got two situations I could get here, just to be clear. I get a full solution where both of these are 0, or I get a simplification where one of them is 0, one of these coefficients. So let's have a look at the coefficients. Well, the coefficient of x to the n minus 1 is this one here, n times n plus 1. Well, that equals 0 when n is 0 or n is minus 1. Now if I look at the coefficient of the power x to the power n, so I'm going to get next, I get this one up here. So I've got 4n plus 1. Well, when's that going to be 0? When n equals minus 1. Now in this case, you can see there's a common solution to both of these equations, which is when n equals minus 1. That would actually tell us that we've found a solution, generalized solution, which is y equals x, a to the over x, wouldn't it? There we go. That would give us one solution to our problem here. In other occasions, we might only just get a simplification. We might not get a full solution. But once we've got that, we can look at using a substitution based on this here. So how's that work? Well, if I know that that's a solution or simplification, I can use this substitution here, y equals z x to minus 1, where z is a function of x. So what do I do next? Well, I could differentiate that using the product rule, and I'll get dy by dx. I can differentiate it again using the product rule or Leibniz theorem, and I get this here expression. And what am I going to do now? I'm going to substitute those expressions, I'm going to substitute those expressions into my differential equation. So I'm going to replace dy by dx by the second expression. I'm going to replace that with the other expression, and finally I'm going to replace my y with that, the substitution itself. I'm now going to group these up. I want to group them up by the order of the differentials. So I've got a differential in dx by d2x by dz, I've got some dx by dz's, and I've just got some z's. So I'm going to start grouping those up. If I do so, I get an interesting effect. Excuse me. I only get one term which has got a d2x by dz squared. You can see here that if I look for what it's multiplied by, well, I had an x out front and I had an x minus 1 there. So I just end up with a nice simple d2x by dz. There we go. And that's just going to come down here into my simplification to give me my first term. What's going to happen with my dz by dx's? Well, I'm getting quite a few dz by dx's. I'm getting 1 from here. I'm getting effectively 2 from there. So I've got 3, and I'm going to put those coefficients into a bracket. There's my bracket. Then what have I got for my z's? Well, I've got a 1z coming from here. I've got a z here. It's effectively got a coefficient with 2 terms in there, and I've got another z from here. So I've got 4 of them there, haven't I, in my bracket? That's my coefficient. Now, given we chose the n to be minus 1, we start seeing some simplifications going on. So let's start by looking here at this coefficient here, where you can see I've got, in the first here, I've got a minus 2x to minus 1. The second term is plus 2x to minus 1. So those two are just going to cancel out. So what do I get left with here? Well, I just end up with a minus 4 dz by dx. So everything's nice and neat, and it's homogeneous. So we're all in business, aren't we? So I simplify in its simplest form with just constant coefficients. Let's have a look at what happens to the powers of z. Well, actually, because we had a full solution, I'm going to get 2 cancellations. I've got cancellation here with that 2x to minus 2 with that 2 term there. And I'm also going to get cancellation of this term here with that term there. So I end up here with 0 lots of x. Now that isn't always true. You know, I could have some constant term of x in a lot of equations. If I haven't got a full solution, I would get a cx instead. But in this case, I haven't, because that's just cancelled out. So what happened? I've got a nice, simple, well-behaved second order diff. What happens? Well, I know how to solve that. I use my auxiliary equation, find my roots of my auxiliary equation, and I get a solution in terms of z. This was a differential equation in z, wasn't it? So here I get z equals a plus b e to the 4x. Why have I got here? If you think about it, that's an e to the 0x, isn't it? Here in the first one. And that's in terms, so I've got z in terms of x. Of course, I need to get back to y, so I use my substitution again. Y equals z lots of x to the minus 1. And hey presto, here's my final solution. So I got a general solution, didn't I, for that using this method. So let's just summarize then, so you can take notes, pause the video, take a note of what I've got here on my summary. I can take an equation with lots of different degrees in it. I can try and find a solution in terms of y equals x to the n, or a simplification, where I get rid of some terms by picking the right value of n. If I can do that, if I can find some values of n and it works for, then I can use that as the basis of a substitution, y equals z times x to the n, and if that, and use that to simplify my second order differential equation to a nice, well-behaved differential equation. I solve that for x, so z, sorry, in terms of x, and then I need to get back to y, so I use my substitution to get back to y. So there you have it. If you're going to get a solution from the, you can find an x to the n, then you can use this method. Best of luck.